We will talk about reinforcement learning in finance today. Yeah, thanks for being here.
Yeah, okay. So my presentation today will focus on some insights I derived on what I would call the current state of reinforcement learning in finance. We'll make us a few more kind of constraints and definitions of what we mean by that in this presentation. But for the general agenda, click on it. Yes, we're gonna start with the key insights. So I'm gonna just give you the takeaways right at the beginning, so you know what to remember. Then we will go into details, starting with some preliminaries to understand the research itself. Then I will present evidence for insight number 1 and evidence for insight number 2. Then we'll draw some more general conclusion about the current state of the field. And then I would like to end on a more constructive note about asking, okay, what can we also do differently, or how can we improve? And the key insights are basically that RL in finance is currently focused on model-free algorithms, mostly applied to equity markets for allocation tasks and evaluated on simulated backtests. This is kind of the first part. So if you're not sure what these terms mean, we will get into that. So no worries there. And the second part is RL in finance suffers from recurring methodological weaknesses in code and data sharing, reporting of hyperparameter tuning, and reliance on train test paradigm for generalizability, despite potential non-stationarity concerns of financial markets. So I said these are kind of the key insights right at the beginning. If you only want to take away something from this presentation, it's that slide. If you want to understand in more detail why I think that is, you should know, keep paying attention. So from the data side, what did I do for my SLR? I started out with 543 query results from Scopus. Here you see kind of the flowchart. In the end, we had 163 studies after screening. 160 of them were kind of experimental empirical papers, and 3 of them were literature reviews. So you're going to see most of the data that I present only pertains to the 160 and not to the 3 literature reviews. For reinforcement learning, I think most people are familiar with the concept. Just to agree on kind of a terminology for this presentation. So we roughly differentiate between model-free and model-based. And the model-free part is basically we have an agent that takes actions in an environment and receives a reward in an updated state and kind of learns from that. In a model-based RL, we include kind of model learning where the agent tries to form a model of an explicit model of the environment. We don't have to go into the details for this presentation, but just to have in mind that there are these 2 approaches helps with understanding the results. And when I talk about applications or financial applications, I refer to what has been identified in the previous literature review, where they basically outlined the following applications in financial markets. So algorithmic trading, portfolio management. In this case, there were some other which didn't fit that framework. Then market making, optimal order execution, and option pricing. And what we can already see that in the corpus that we've extracted, most of the studies either focus on algorithmic trading or portfolio management. Whereas option pricing or optimal order execution receive, or also market making, receive very little attention. Then, go a little bit deeper into insight 1. I claim that RL in finance is focused on model-free algorithms applied to equity markets. So equity in this case means another word for stock. So you have ownership in a company, and it's not like a commodity or a bond or some kind of debt instrument. And then allocation tasks. So also in the SLR, which we're not going to go into detail in this presentation, we map these previous applications to specific decision-making tasks, which we differentiate between allocation, prediction, and execution. We can also in the Q&A part go deeper into that if you're interested, but for now we'll leave it here. And they're mostly evaluated on simulated backtests. So that means they take historical data, split it up in a train period where they train the model, and then an evaluation or test period where they then evaluate the trained model. and then try to make conclusions about the performance or generalizability of what has been learned during the trade period. So it's basically in sample, out of sample performance.
Model 3,
Yes.
is that obvious, or what exactly is that?
How I define, know if it's model
Yeah.
or not. That was decided based on the algorithm that they specifically used in the respective papers.
What is a Model 3 algorithm?
Yes, so for example, you mean like want a general definition or an example of what a model 3 algorithm is?
Whatever you prefer.
Okay, maybe the examples are easier than a general definition. I would say an reinforcement learning architecture that mainly learns from the observed data itself, just from observations,
Yeah.
without forming the model. That would be, for example, a deep Q network would be just a Q network.
So what I always have in mind is you can do regression, and then you have a model where you do least squares, and it's Model 3. It's the same estimation procedure. So sometimes it's also depend on your optimality claim, whether something is model. Okay.
All right. Okay. So
There's someone waiting in the lobby.
Yes, I think Wouter might be able to let the person in. Okay. All right, then, Model 3 algorithms. So we see they mostly use actor-critic, value-based, and policy-based methods. And those are the explicitly model-based methods are a lot rarer, as claimed here. So then when we look into the markets, we see that the data used are mostly stocks or equity. Then, interestingly, I think the second is crypto, which is relatively new kind of financial instrumental market, if you think about it. And then a lot less prominent, we see derivatives, commodities, kind of non-crypto, so foreign exchange currencies, and then unspecified/other types.
Derivative, that like options? Or?
Yes, basically options, anything that is based on an underlying. Then to the task itself. So we mapped these applications that we showed in the beginning to 3 types of tasks. First is what we defined as an allocation task. That basically means that the agent has to make a decision of allocating some kind of budget. So that would be usually a portfolio management or algorithmic trading, where you have a certain amount of cash that you can allocate or not allocate to a certain asset. Then the prediction task is something like predicting the directional movement or general forecasting of the time series itself. And execution is a specific case which might not be super intuitive for if you're not familiar with kind of finance. But the idea here is that you have to have kind of an order quantity that you want to sell off a certain amount of a stock. And if you sell it all at once, you have a market impact. And the idea behind execution is how do you basically schedule your orders in such a way that the market impact is reduced.
So it's like an extension of allocation, but taking into account another objective?
Yeah, so usually that's another thing. You can split them between prediction, which then usually you often need a prediction to then downstream make an allocation decision. And then the allocation decision leads to orders, right? That you have to then do. And you could then use execution strategies. But it's not necessarily the case that every implementation that does allocation also does execution in the sense of having a specific RL model that optimizes it. So for example, many tests just assume, okay, we have an allocation task where we say, for example, we have the Dow Jones Industrial Average as constituents, so all the stocks in that index, and we can trade them. And the assumption is just there's no market friction. You can always buy and sell whatever you want. This completely leaves out any problems you would have in the real world with execution. So this is one of the kind of simplifications they make in those backtests. Okay, then implementation status. This is what I was now meant with the backtesting part. These are basically simulations. You use historical data, but you don't really test it in the real world. Actually, I think there's been 4 or 5. I don't remember the exact number. Studies where they actually took their reinforcement learning agent out of, I would say, simulation development and tested it against real world data in an environment. and also with actual money at stake. So in general, what you see, pretty much all studies only concern themselves with historical backtest, report the performance metrics, and then kind of usually they say, yeah, this is an indication for research and practitioners and so on, but they stop at any kind of real world application. And yeah, that is the first insight, or kind of group of insights. The second is more on the methodological side. Here we see that it has recurring weaknesses in code and data sharing, the reporting of hyperparameter tuning practices, and reliance on the train test paradigm to basically train in-sample, then validating out-of-sample for generalizability, despite potential non-stationarity of financial markets. For the code and data sharing, I think this is relatively easy to understand. What I did is I looked into all of the 160 empirical studies and just checked how many of them actually shared their code transparently and accessible. And the first thing here is that out of 160, only 17, so a little bit more than 10%, actually shared their code. And then we looked into some kind of reproducibility criteria. The first one was kind of rerun as is. So can you actually rerun the code that they provide with the same code, same data? That seemed to work for 14 out of 17. So that's like an 82% out of the actual ones that share, and 8.8% of the total studies. Another one is, could you rerun it with updated price data? So we assume something like same code, but new data. Say, for example, they published their paper in 2022, and now we want to see, can we rerun the whole thing with data from 2022 to 2024? And what we were looking there was mostly, okay, did they, for example, use an API where you just change the date and then rerun it to get the fetch new data, which would be an easy and practical implementation to verify yourself, does this actually work with future data as well? Then the other next criterion was rerun with custom data. So that would mean maybe they trained it on Bitcoin, for example. Can we replicate it with Ethereum or something like that? Then you would either, for example, switch out CSV files or change, if it's using an API, change kind of the variable value, things like that work. And here we see kind of updated data was only 2 studies. Custom data would work with 12. And then there were 2 where it's just for completion. The code was there, but it led to either a misleading or kind of broken GitHub repo where basically there was no data or not identifiable. Yes, so much for kind of code and data sharing practices. So why is that so important? In my opinion, it's very important because you see a lot of claims in the papers themselves, and they of course have to use the code to generate the evidence. And I think it would be relatively easy to share the code, which then actually allows you to test whether the evidence is generated as they claim. So it's just basically a matter of transparency.
How's the third line? It seems more ambitious than the second one, but there are 12 who do it. It seems easier to do 2 than 3.
Yes. So the reason why I had this is because the way we checked it was that custom data means they have, for example, also CSV files as input, and then you could just switch out the CSV file. Yeah.
Same time frame and so on.
Yeah, same time frame.
Okay.
Just change the CSV file to another, basically a variable or financial instrument. Okay. Then hyperparameter tuning. This is also a transparency thing. It's not about how they specifically did the hyperparameter tuning, but rather did they, in the paper or in the code whatsoever, describe how they tuned their hyperparameters, or if they even did it. And we see here, I think a little bit more than 120, there was no description of hyperparameter tuning versus roughly 40 actually described it. So why do I think that this is a methodological problem? If you don't describe hyperparameter tuning, you don't really know if certain improvements might actually come from the just exploring more in the hyperparameter space rather than algorithmic or kind of architectural improvements that you might claim. So also, if you know the hyperparameter tuning procedure, it's easier to understand how many iterations they ran to come up with the results that they got. So there might also be a risk of cherry picking if you don't really know what hyperparameters or how the process was done. Yeah, the next one is the non-stationarity aspect. So here, why do I emphasize that? In other domains like games where reinforcement learning originates from, or also now robotics, where it seems to be more and more successful, you assume that the environment that you interact with is somewhat stable, that your training distribution is the same as your validation distribution, or when you then apply it, which is also called the sim-to-real gap in some parts of reinforcement learning literature. And I think in financial markets, I would phrase it that way, there's no concrete evidence that the distribution or the data set that you train on is actually similar to what you then will deploy it on later. I think that also has to do with, to some extent, our limited understanding of what actually is a financial market, what are the dynamics, can we assume stationarity or can we not? And here I just show that at least there's some lack of awareness of this potential problem in the literature under review. So what I would conclude from the evidence provided plus 2 insights, that we saw a lot of papers, like 160, so it seems to be very experimentally active. So a lot of people trying a lot of different experimental configurations, but it seems a methodologically stagnant research field. So as we refer here to a paper, which is related to references that you can look into if you're interested, it is actually from Moody and Safler from 2001. So that's even before kind of reinforcement learning got really big and before we even had deep neural networks. But back then they already applied this kind of standard methodology of, I take a historical data set, I have my reinforcement learning agent, I train it on an in-sample test set, in-sample training set, and then later validate it on the out-of-sample set. And what I want to highlight with that is that now 20 years later, or more than 20 years later, the methodology, even though the weaknesses that already have been acknowledged in that paper are still the exact same. So there is a lot of experimentation, but there's no improvement in the methodology used to conduct the experiments. That's how I would phrase it. And I think that leads to the second point, that the literature is somewhat fragmented and not cumulative. What I mean by not cumulative is that you would expect that if a lot of people over time spend a lot of energy into researching a problem space, that there would be some kind of improvement over time and you build knowledge on top of each other. But my interpretation of the literature is that basically different people come in from different angles, try more or less the same methodology in a specific sub-problem, but this doesn't connect to the general body, and then there's no kind of emergent higher level understanding of what reinforcement learning and finance actually constitutes beyond this kind of experimental activities. And from that, I also conclude that methodological progress seems necessary to advance. Of course, that's very easy to say that we should maybe improve the methodologies, but what does that mean? And that's why I also want to bring this presentation to a conclusion with a bit of an outlook. So that's also what we propose in the SLR itself, a roadmap, which has 6 steps. The first one, which I think is very straightforward, is improve reproducibility. That refers also to sharing the code. So it should be relatively straightforward to openly share the code that you use for your experiment. This also should increase the trust in your results. Then the second point is standardizing tasks. So we just touched on it, but we've seen that there are many different kind of applications. And this was just the definition that they used in that one systematic literature review. That doesn't mean that the whole field agrees on that. And so what we often see is also, or something that I ask myself, what is the difference between portfolio management and algorithmic trading, or trading 2 assets and managing a portfolio of 2 assets? kind of from a finance practitioner side, you could argue, yeah, portfolio management is more long-term, strategic, and algorithmic trading might be more tactical, short-term. But is that really something that a reinforcement learning agent kind of necessarily understands or needs to distinguish in that sense? Or is it from a kind of decision-making perspective more like you have different assets that have time series generators that have distributions or some kind of pattern, and you just try to make allocation decisions? So we're taking things from finance and reinforcement learning, which are different or evolved independently, and then just kind of trying to fit them together without really having any kind of standardized tasks there. Next one is standardized reporting. Something I didn't cover in the presentation, but is also in the SLR, is that they use a lot of different metrics to evaluate the models, and they also depend on the task and so on. But I think we have like more than 100 different metrics recorded, and sometimes they also don't specify the mathematical definition of a metric in the paper itself. So I think one funny case was that there was cumulative returns in one paper without the definition, then the next paper has cumulated returns. Now the question is this the same? Do they mean the same? Do they have different calculations? But you don't know. You just see the term in the table with a value, but you can't really compare anything from that. Next thing is then also standardized data sets. I think this also touches on the other two beforehand. So the overall comparison is not really easy or even possible if you have one, say, multi-asset algorithmic trading on Bitcoin from 2018 to 2023, one paper. The other paper is portfolio management of S&P 500 from 1985 till 2015. And then they also use the different metrics. And now you try to assess, does this reinforcement learning agent, maybe they use the same one, kind of consistently perform well or not? How do you draw any conclusions from that, right? Then increased realism. That's something I also want to show on the next slide in more detail. Then we came up with something called the deployment ladder. And then if all those things are implemented, or to a certain degree, you might also be able to introduce a kind of taxonomy for the research efforts, which then helps to structure also maybe which areas are underexplored and which are maybe a little bit saturated. As you also seen in the beginning, a lot of work already focuses on portfolio management, algorithmic trading, and model free. But maybe there's a lot of opportunity in a field like market making with a model-based reinforcement learning algorithm. And yeah, the specific example here for the fifth point, what we call the deployment ladder. So usually we see people in their work starting here historical backtesting, and they stay limited to that stage. The problem here is that you assume that when you have positive results, that the positive results come from your reinforcement learning agent having learned something from the data. The problem is you don't know if there's actually something to learn in the data. So there's a lack of ground truth. And what we propose is actually to, before doing the historical backtesting on real-world data, take a step back and use ground truth generators where you actually know whether there's something to learn or not. So for example, if you test it on a random walk, there shouldn't be anything to learn as there's no signal. Versus if you have something like a noisy upward trend or some noisy periodic trend. And of course, these patterns are stylized, but you can at least test if the algorithm in general has a pattern learning ability. And then having verified that, you can at least have more confidence in the historical backtest results. So that would be the first step. Basically a step back and then forward again. And what we then see is also not stopping at historical backtesting, but for example, deploying it in what's called paper trading. So basically, you deploy it in a live simulation where it uses real world data, but no real money. So it's like kind of a fake account. There's a lot of online broker APIs that offer that. So from a kind of practical perspective, this should be feasible. And then, of course, as we kind of move up the deployment ladder, it gets more and more mature, where then actually is like actually deploying software in a real business. To what extent this then actually should be done by researchers alone or in collaboration with companies, financial or investment funds is of course up for discussion, but I think this at least shows kind of the maturity progress we would expect from a reinforcement learning implementation in finance. Okay, this was just one specific example to show you, okay, how something or these problems could be tackled. Yeah, the reference I said this Hamlet all the as I think very good systematic literature review. This one's the paper from 2001. If you're interested in the field in general, I recommend reading this paper first, and then reading all the kind of current stuff, and then think about, okay, is this really much different than what they were doing back in the days? And yeah, here just for completion, our preprint currently available on SSRN. Okay, thank you for your attention. We already discussed some questions, but are there any other questions left? Yes, please.
So this is part of your PhD journey, I suppose, right? So what are you going to do based on that?
I would go to the slide again to answer the question. So for my own research, the question, of course, now is seeing kind of these limitations, do I have ideas to work around them? I think one big problem for directly applying reinforcement learning to finance is not reinforcement learning, but finance. So also the understanding, okay, what is a financial market? How do you model a financial market? I think that's a very big problem. So what I'm moving now towards, to a certain extent, is trying to kind of abstract or make it a little bit more abstract and try to understand what is temporal learning, for example, reinforcement learning agents. So learning structure from only temporal data. And how do you know if you actually learn something from temporal data, or if you're just kind of fitting to kind of some spurious correlation? And so this is also what I'm currently working on. I guess in the future I would like to make another presentation where I can show that in more detail. But I hope for now this is a satisfactory answer. If not, I can also try to expand a little bit on that. Okay, so basically somewhat in that area, I would say. Okay. Any other questions? Yeah.
Suppose you find a very good algorithm, reinforcement learning. Will it be published or not? Is there a kind of publication bias? That's maybe one of the aspects in finance that's also a bit tricky. If it really works, it's not public.
Yes. So basically to say, it probably would be not that smart if I actually had a money-making machine in that sense to tell it other people.
Yeah, I cooperate on this.
Exactly. So yeah, that's also the question. And I don't expect that the outcome of my PhD research will be to have a money-making machine. So that's also another thing when we said, okay, when I said finance might be more a problem than reinforcement learning. It's kind of the understanding the assumptions and complexities of the domain rather than of the agents themselves. Because as we also discussed, assuming you had an agent, you publish it, and then other people also start to apply it, is there some kind of self-correcting mechanism in markets itself? So what is even our understanding of financial markets? Because how it is usually modeled in these papers is that they assume there's some kind of data generating process, the market. And then your agent observes the data, makes decisions, and in most cases, they don't even assume that there's market impact. So you just make decisions based on incoming data. Now, with what you propose, we actually somewhat qualitatively, as humans say, no, markets actually work differently, right? Because you have a lot of people, kind of a multi-agent system, where everyone observes everyone else, at least to a certain extent, and then also adjusts their own behavior based on what they think the behavior of the other people is. So it becomes like a kind of multi-agent evolutionary game theoretical problem, which is a lot different than this kind of model, problem model. So that's also an interesting thought. I think we don't have a. Sorry for the online audience, but I draw something down here and try to explain it also via sound. So I think there's something like the real world phenomenon, and then you make a mathematical model of that problem, and then you develop your solution, right? This could be a reinforcement learning agent. And then you basically, your agent doesn't solve the real world problem, it solves the mathematical problem. But the assumption is that the mathematical problem is actually a good representation of the real world problem. And basically what we are saying now here is probably the way they model the real world and then solve it is not actually a good fit. So maybe also the question is, do we need to work on this? So the fit between mathematical problem and real world, not the fit between solution and mathematical problem. But of course, there's a lot of big questions here.
Is that relating to your deployment ladder as well? Is that the first stage? Or isn't?
So in I guess the first stage would allow you to test different mathematical problems of the real world because you make them explicit through modeling them. So what you could do is do one generator, which is non-reactive. Basically what is usually assumed. So it just generates data based on, for example, distribution or some function. And then you could take another generator, which is reactive. So it sees the action of the agent and adjusts. And then you could have another agent, which is even more complex, could be another reinforcement learning agent. Sorry, another generator, which could be a reinforcement learning agent, which strategically adjusts, not just deterministically, but tries to kind of outsmart and then becomes a betting game. A game theoretic problem. I think it's called a Stachelberg game if it's one after the other, right? It's sequential. And based on that, you could go even more complex and then make it multi-agent. And then the generator is kind of an emergent property of all the actions from different agents. And the question is, which of these, or maybe also none of these, is a better fit than the current simple generator? So I think what the field reinforcement learning in finance also lacks is kind of conceptual clarity to a certain extent. Yes, I'm not sure if I was able to answer a question or just raise more questions myself, but yeah.
Very sharp question.
Okay. Any other questions?
And thanks again.
Thank you very much.